Here we go. Okay, guys, 2 punches. Here's what we're going to do. Title is 2 punches, but this is really applications of the derivative. It's a little different from what's in the book, so there may be a bit of a struggle to apply what we're doing out of the homework, but I'm hoping it'll help. This is very, very general. First, I need to hit someone in the face. So Joey, come on up. Your turn to be a star. Okay. All right. Now, here's what I need to do. Okay. All right. Stay about right there. That should be good. Okay. All I'm going to do is move my hand twice. I already talked about what a derivative is yesterday. We talked about how to find what the powers rule. But I'm just going to move my hand 2 times. You ready? Okay.
I think he's blocking.
That's okay. I think we got enough. So here's one of it. Okay. First, I'm going to move my hand this time. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi. Okay. Everyone get that hand motion down? You see what I did there? Okay. It's very complicated, I know. Now I'm going to move my hand another time over the same 6-second time interval. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi. Okay, thanks, Joey. Have a seat. All right. Nice reaction, by the way.
What is that?
The bell. The bells are back on. They were off for testing. Okay. We haven't had them for a while. Now, I'm going to graph the 2 hand motions I just did. Thank you again, Joey. And they look like, okay, for the first one, both times I moved my hand about 30 inches in about 6 seconds. Tell me something about the first time I moved my hand.
Slower.
There's a continuous rate, sort of.
Continuous rate. Not quite the right use of the word, but I get what you mean. It was a constant rate.
Sure.
It actually, the rate didn't seem to change. So, if you think about that old rate of change slope relationship I've been trying to hammer lately, I started at moving 0 inches in 0 seconds, and I wound up moving 30 inches over 6 seconds. And if it was a constant rate of change, then I would graph that with a straight line. What would the slope of this line be?
If it was a constant rate of change.
Constant rate of change, but look at the units, don't look at the angle I did it at.
30 over 6, so...
It's your change in y, which I suddenly can't write. It's your, how much did y change? 30 inches. How much did x change? 6 seconds. So, physics kids were paying attention to units today. 5 inches per second is a couple of things. It's the average rate at which I moved over this time interval. It's the slope of this line. And if my fist had actually connected with Joey's chin, with what velocity would my fist have connected with Joey's chin? At any time over that first interval?
It's 5 inches.
5 inches per second.
Yeah.
Yeah, if he leaned to one side, if I hit him at 1 second, I would hit him at 5 inches per second. If I hit him at 4 seconds, which is the point I was really interested in, after about 4 seconds, I had moved 20 inches, if this really was a perfect linear proportion. But the speed with which I would have hit him was 5 inches per second. Anywhere, if I hit him in that time interval. Was the second punch similar to this one?
In what sense?
Well, did it have a nice constant slope? Will it be as easy to graph?
Because it just, you were held and not in.
Boom. How can I, but I did 3 different things actually. I held it still in one position, I moved it, I held it still in another position. Same outcome though, I still started, well, same outcome for where my hand began and ends. Possibly different outcome for Joey's chin. So I've got my same deal of winding up here at 6,30. But I can't really have one line describe the situation. Because as Michelle put it, I held my hand still and then, I haven't timed this lately, but years ago I did this. at about 4.1 seconds. It's probably when I got up to there. So this is just a line of it sitting still. What do you think happened in between 4 and 4.1 seconds on that second punch that I threw?
There's like a
stop
leap.
yourself.
Well, definitely in terms of the position.
It was like a steep jump.
It's like a very steep jump. If you're punching, you're really trying to accelerate. You're really trying to, I mean, it went from 0 and it really went as quickly as I could get it. What kind of functions do we use to describe accelerations in physics? What do we use? Everything that accelerated was what type of equation? It was always the same thing. Think about gravity.
Quadratic? Exponential?
No, it wasn't exponential. That would be,
Wait, no.
you would trip, fall, and die if it were exponential. Yeah, it was always quadratic. All the displacement, all the changes ones. So if you're really trying to accelerate, we'd have to fit a quadratic function into here. In other words, this is piecewise. This is going to be, thank you for rolling with me on that one. I don't feel like I was asking those questions well, but you guys got what I was going for. From the time being 0 to 4 seconds, what describes what my hand was doing? How would I describe that as a...
F of x equals 0.
It'd just be 0. It's a horizontal line along the x-axis. There's nothing going on there. From 4.1 to 6 seconds, what describes the equation of my hand's position? Went up to 30, and then it just stayed there, right?
Yeah.
So how do I describe a horizontal line there? Y equals
30.
30. That's all I do. Y equals 30. In between, this is what I'm interested in. 4.1, oops. That's what we're curious about.
Wait, wouldn't it be 2 because you're like accelerating and you're also decelerating, so wouldn't we split that into 2?
Ideally, but I'm hoping that if I punched correctly, the deceleration at the end was so fast we could ignore it. And also, I don't want this to be a really breakdown engineering physics lecture of everything that really happens. I was going for a quadratic acceleration, I was trying to stop quickly, and we're going to pretend I achieved those goals just for purposes of time. All right, Joey, can you turn the camera to face this board now? All right, here's the interesting part.
Wait, so we don't know exactly what's happening.
We're going to I'll show you a trick for figuring that out real quick. We're going to come up with that model right now. And it's going to be very, very oversimplified for reasons Joey already mentioned. What does this symbol mean in an x-axis, in a graph?
It means there's a lot, yeah.
Yeah, we skipped a break. We skipped a bunch of stuff. You're allowed to do that as long as you put that symbol in. And I'm not going to care about anything other than 4 to 4.1 seconds. Now, as Joey remembered, we'd like to use quadratics for accelerations. So I went from 4 on the x-axis to 4.1 comma 30. And we're going to assume I did it with some sort of parabola. Yes, we should break it down again and do my deceleration. No, we're not going to do that right now. There's a flaw in this model, but I think this would be good for our purposes today. Super quick parabola review, because we didn't spend as much time on this as I would have liked, and I'm going to walk you through this one. You should have done this in Algebra 2, but it may be a review. Do you guys remember seeing vertex form of a parabola looking something like that? Actually, I've been using H and K the other way all year, so I'll be consistent with myself. Okay. K and H tell you where the vertex is, right? Now this is where I started accelerating, so that's going to be my vertex. So what is the vertex of this parabola?
It would be, wait, K and T is the opposites. Would it be
4,
negative
0.
4?
Yep, negative 4, 0. I don't have to write the plus 0, but let's leave it there for a sec. I don't know what this a value is, but so I'm just going to leave this f of x for now. The way you would find this a value, to go back and just review this a bit, is if you know another point on the parabola, you could plug that in for x and f of x and solve for a. Do we know another point on this parabola?
Oh my gosh, we do.
Oh my gosh, we do. We know that 30 equals a times 4.1 minus 4 squared. What's 4.1 minus 1? Minus 4, excuse me.
0.1.
0.1. May I write that as 1/10?
Sure.
What's 1/10 squared?
1/100.
1/100th. Multiply both sides by 100 and a equals 3,000. So I'm going to say between 4 and 4.1, we're going to model what I was doing with my fist, the position of my fist as it accelerated. We're going to model that with f of t equals 3,000 x minus 4 squared. I didn't even ask you guys a question yet. Here's my question. If this model is accurate, or based on this model, at the exact instant that my fist hit Joey's chin, which it really didn't, we're pretending, what was the velocity of my fist? What was the speed in that moment, that infinitely small chunk of time right when there was contact?
Wait, so then we use that derivative thing you talked about.
It's that derivative thing we talked about. See, what I'm actually looking for, believe it or not, remember we follow me back this way a second. Average rate of change. You guys were very quick to notice that if I had hit Joey on that first punch, no matter when I hit him, it would have been 5 inches per second because my fist was just moving at 5 inches per second the whole time. If all you do is move at a constant speed, it's very easy to figure out what happened with like a collision, for example. You've been doing problems like this for years where things have been moving at constant speed. A train goes in one direction at 50 miles an hour. A train goes in another direction at 60 miles an hour. After 3 hours, how far apart are they? Remember those from middle school? Car goes 50 hours. Car goes 50 miles an hour for 6 hours. It's gone 300 miles. Do cars in real life just do that, though?
Yeah, they go faster and slower and they stop
They
sometimes.
go faster, they go slower, they stop sometimes. You stop at a rest stop, you have a Cinnabon, you use the bathroom, you get out, you hit a tree. You know, cars do all sorts of things. And I mean, I have a friend who Noah was doing a senior project with, who is a forensic engineer. He looks at accidents and he tries to figure out what happened. Do you think he'd be very accurate if he just assumed that the car just kept moving at the same speed? Okay, so if you have an accurate model for position, it's your equation. Follow me back over here now. The derivative of this model tells you velocity. Let's talk a little bit about why that's true, though, for a second before rushing to find the derivative. If I want to find out how fast my fist hit Joey's face, could I just use my average speed from 0, 0 to 630 again, like I did on the first graph? Would that be very useful? I think I hit him at 5 inches per second. No. Would it be better to take an average speed from 4 to 4.1?
Yeah.
It would be much better. It would be. So the average, let's write it this way. Now, that average velocity in this case, because this is a displacement graph, that's going to be my slope. And my slope from 4 to 4.1 is just going to be, well, where was I at 4? I was at 0. Where was I at 4.1? I was at 30. That was at time equals 4, and at time equals 4.1. So I'm going to get negative 30 over negative 0.1, which is positive 300 inches per second. Does secant or a tangent line?
Secant.
Secant, it's cutting across, it's taking a short cut, and secant is Latin for sever. So that's not super useful. That's not huge. It's probably closer. I was probably even closer to 300 inches per second than I was,
Wait, how is negative 30 over, wait, so negative 30 divided by 0.1 is 3.
well, they're both
That makes
negative.
sense,
Yeah,
yes.
it's 1 divided by 1/10 is the same as multiplied by 10. But double check me. All right, what would make this more accurate? If we use the whole 6-second time interval, we get a ridiculously low average.
You could get even more exact and do like 4 point, I don't know, whatever, like in between 4 and 4.1.
Let's keep moving by tenths. Let's go, how about, let's go to 4.09. So what this is gonna be, so that would be the slope from there
that's
to
by
there.
hundreds, that's,
Yeah, does it start, and is this, now this is still a secant line, right? But what is this starting to look like it's getting closer to being?
tangent.
A tangent line, thank you for remembering that. I don't feel like I'm asking great questions today, but you guys are right with me. So now, the slope from 4.09 to 4.1, I'm gonna write this a little differently. It's gonna be my function at 4.09 minus the y value of my function at 4.1 over 4.09 minus 4.1. What happens if I plug 4.09 into here? Anyone got a calculator handy? Two of you have seen calculators on your desks.
Wait.
Right. Well, what is
So what are we plugging? We plug in,
4.09 into our function? Well, what's 4.09 minus 4?
Point.
Yeah, f of, we can get a little further with this without the calculator. Back now, Michelle, I'm motivated, don't tell me
I
yet.
have a,
Don't tell me yet. You hesitated and I got motivated.
is this
4
a
point-
waste of time, Mr. Donovan?
Oh, not yet. 4.09 minus 4 is just 0.09, right? And that's squared. So that's 9 over what?
100.
0.09, that's 0.008 once.
Right. I'm gonna go, so you guys go ahead and tell me this. What is this?
It's, oh, I mean,
24 point,
Oh, yeah, that's what I
Three.
24.3.
Yeah.
Okay, so this will be 24.3 minus, at 4.1, we know it's at 30 because we picked that point to be the end, over negative 0.01, correct? So that's negative 5.7 over negative 0.01, positive 570 inches per second. So if we take the average over the whole 30-second interval, you would have to assume that I hit Joey at 5 inches per second. Did it look like I was moving faster than that on the second punch?
Yeah.
Okay, if you look at the whole time the punch was moving, and this equation's accurate, but if you look at the whole time the punch was moving and the 1/10 of a second is accurate, we're looking at more like 300 inches per second. Okay, Joey, is this part still in the frame?
Yeah.
Okay, I hope Tyler can see it. If you look at the last 1/10 of a second, we're at 570 inches per second. I want to go on one more. Two more, actually. What's the slope from 4.099 from 4.099 to 4.1 going to be? Well, it's going to be
It's just the function of 4.00. I get 9 minus function of 4.10 divided by 1.099 minus 4.1. And we just plug in the 4.0.
and let's see what we get. I think I've set that up right, correctly.
You got 29.9
.403, good, minus 30.
divided by, 0.099. Negative point oh.
Minus 4.1, it should be
Wait,
0.001.
sorry. Negative point oh oh
0.001. Is that right? And what do we get in this case? What's this answer look like? This part's just distracting me now because I started to figure it out on my own and then didn't roll with it.
Wait, you get 597.
597 inches per second. Okay, take the whole 6-second interval for this activity, and we have 5 inches per second. That seemed ridiculously slow. Go to a tenth of a second. We get 300 inches per second. That seems more reasonable for a fist flying as fast as someone can throw it. Look at the last tenth of a second. We jumped to 570. But now, we went to the last hundredth of a second, and we're only jumped to 597. Okay? So we didn't jump as much. What do you think will happen if we keep going?
So, it's just gonna increase by a very small
It's gonna get stagnant because eventually it slows down.
That's a smart way to look at the physics of it. I'm seeing more just the math. What do we call it when it's getting closer and closer to something? Possibly.
Oh, what's the word?
Closer?
When a function approaches a
Oh.
dotted line that doesn't, it keeps getting closer. Asymptote. Okay, this seems to be approaching an asymptote. Or perhaps even a limit.
Joey's face.
The limit as we approach Joey's face. One more, guys. One more, 4.0999.
Here, I'll start.
Yeah. Everyone should be practicing doing this on the calculator just because it's surprisingly, it will come up.
Okay, so, you get 29.9400.
29.9,
4003 minus 30.
over, it's gonna be negative point.
Negative. I got negative 1 times 10 to the negative 4. So,
4 spaces, 3 zeros.
minus. You get 599.7.
599.7 inches per second. From 5 inches per second over the longest interval, which is really meaningless, that 30 seconds, when to talk about this punch. 300 inches per second for an average speed over the whole tenth of a second of the punch. The last hundredth of a second goes to 570. After that, we go to 597, and going out to the 10,000th of a second, we only go from 597 to 599.7. Does anyone have a guess as to what number this is approaching?
600.
If I had to guess from this data, I would say that and this model is accurate, if it is, I would say that my fist would have hit Joey's chin with about 600 inches per second of velocity. Is there any way we can check for sure?
Punch Joey.
Punch Joey, how fast did that feel? Joey, follow me back to this board. Well, this all depends on the accuracy of this model.
I guess we can do what we did last night.
Which was, bingo. Here's another thing. See, normally, when I do this lesson, I haven't shown the kids the shortcut yet. But you guys have seen the powers rule as it plays out.